Hello and welcome to a new video on the Crypto2 YouTube channel. In this video of the Basics of Cryptology series, I want to discuss what hill climbing is and how we can use hill climbing for cryptanalyzing classical ciphers. I structured this video into different parts, and in the first part of cryptanalysis of classical ciphers using heuristics, I want to show you what is a heuristic. And after that, I want to show you in detail what is hill climbing and its basics. And as you can see here, we have two different topics also. The first one is a genetic algorithm, which is another heuristic that can be used to break classical ciphers. And then I think I will make a video on simulated annealing, which is an improved hill climbing. And in this video, probably in the future, I want to show you how you can improve hill climbing with simulated annealing or other techniques. But first of all, let's have a look at this slide here. You probably remember this slide from my other videos. And as we already know, cryptography is the art of making ciphers and cryptanalysis is the art of breaking ciphers. And in this video, we want to have a look at cryptanalysis. In detail, we want to have a look at cryptology, cryptanalysis, and I marked here in green classical and modern cryptanalysis. And hill climbing is a modern technique to break classical ciphers, but it's also inspired by classical cryptanalysis like frequency analysis and so on. So I think that the topic fits to classical and modern cryptanalysis. And I could also have marked in green the cryptography and classical and substitution and transposition, since these are the ciphers that we want to break with hill climbing. So what is a heuristic? I took a nice definition from the English Wikipedia, so I'll just read it. A heuristic technique or a heuristic is any approach to problem solving or self-discovery that employs a practical method that's not guaranteed to be optimal, perfect or rational, but which is nevertheless sufficient for reaching an intermediate short-term goal. Where finding an optimal solution is impossible or impractical, heuristic methods can be used to speed up the process of finding a satisfactory solution. And in our case, our problem is that finding the key of a classical cipher with brute force is mostly impractical. For instance, with a monoalphabetic substitution, of course we could try to search for the key, but since we have 2 to the power of 88 different keys, this would take very long time, and I think we all would not reach the end of the search. And the question now is, can we speed up the search for the key using such a heuristic? For instance, making the search then practical. And we can answer this in short with yes, of course, we can use heuristics to improve the search for a key. In our case, in this video, we will use hill climbing. Because hill climbing is a well-suited heuristic to do so. And why is it such a well-suited heuristic, we will see on the next slides. But first, before we start using hill climbing, we need to know the vulnerabilities of classical ciphers, which we want to exploit with hill climbing. And I tried to find the most important vulnerabilities of classical ciphers, and I came to a list of 4. And from now on I focus on substitution ciphers, but you can also use hill climbing to break transposition ciphers also. And we have 4 different vulnerabilities. First, letter frequencies are still visible in the ciphertext. And then, but this comes from modern cryptanalysis, is that low diffusion after changing the key or plaintext. Then the third one is that we can measure how good even a wrong key is. What this means we will see on the next slides. And of course the fourth vulnerability is that the inventors of historical or classical ciphers didn't know computers. So we make a lot of advantage using these. So let's come to the first vulnerability, that is letter frequencies are still visible in the ciphertext. And when you saw my previous videos, you should know this. Here's an example, for instance, a simple monoalphabetic substitution cipher. Here we have, this is a test of the monoalphabetic substitution cipher as text, and then it's monoalphabetically substituted. And as you can see here, we have the ordered plaintext frequencies and we have the ordered ciphertext frequencies. And with the monoalphabetic substitution, of course, these stay the same. And even with other classical ciphers like the Vigenère cipher, this also holds true, that These frequencies can be seen in the ciphertext. The second vulnerability that we have is low diffusion after changing key or plaintext. And here I have an example for this, what this means. So we have here a text. This is a test of the monoalphabetic substitution. And we have here a key. And this here is an encrypted text. And now we change the key by just changing 2 letters in the key here. So the X and the I we change here. And then you see that in the ciphertext we do not have many changes. And in this example only 9 letters changed in the ciphertext. And this is about only 17% of the letters. Modern ciphers change on average about 50% of the bits when the inputs are changed. So 50% of the ciphertext is changed. But with classical ciphers, only small parts are changed when you change the key. And then we have our third vulnerability. That is that we can measure how good even a wrong key is. And what does how good mean? So we have so-called fitness functions that rate the decrypted plaintext based on a key. And the cool thing here is that the better a key is, the higher is its fitness value. And I have here an example for bigram log2 cost function of Crypto2, which I performed on the decrypted text. And here, this was also a monoalphabetic substitution cipher. And here you see the key. So we start with a more or less random key to decrypt our text. And then we computed the bigram log2 cost function. And we get this value here. Now I improve the key, so I make it better. I know what the original key was, so I just exchange 2 letters that I get closer to the correct key. And as you can see here, the cost value increases. And then I do the same here. I exchange also 2 keys and I get a better cost value. And then I do this again with these 2 letters here and it even gets higher. And in the end, with the final correct key, I get the highest fitness value. And this is a huge thing that we can use when we are doing hill climbing. And the last vulnerability on my list is that the inventors of historical and classical ciphers didn't know modern computers. For instance, with Crypto2, we can achieve 120,000 keys per second with our Visionaire analyzer on a single CPU core. So 127,000 keys means that 120,000 plaintexts are generated based on different keys, and these can be used to analyze and to increase our performance. And this high speed of key performance enables us to use optimization techniques like hill climbing, like simulated annealing, genetic algorithms, and so on. And another neat thing is that we can also use parallelization and distribution to additionally speed up our analysis. For instance, instead of using only a single CPU core, with modern computers we can use 4 or 8, or with big servers we can even use more. And with distribution I mean that we can use clusters. Instead of only using 1 PC, we could use 10 or 100 or 1000 PCs. And this also increases our analysis speed. So after having a look at the vulnerabilities, we could just ask ourselves, why not just test every key? That means we search for the correct one via a brute force attack. And how do we do this? We just decrypt every key and rate all the keys, and then the best of course should have the highest rating. But here's the problem. With even a simple cipher like the simple monoalphabetic substitution, we can achieve about 120,000 keys per second with Crypto2, for example. But what is the computation time to search through all of the keys? We know that the simple monoalphabetic substitution has a key space size of 26 factorial, which is about 2 to the power of 88.4 keys. So let's compute the search time. We divide our total amount of keys by the speed that we have for a single core. And then we get about 2 to the power of 21.5 seconds, which is about 2 to the power of 14 years. And yeah, maybe brute force is not a good idea to analyze a monoalphabetic substitution cipher. Even using huge computing clusters, this takes too much time. So we need something to increase or to optimize our analysis, and this is hill climbing. So what is hill climbing? Here is a basic algorithm with 8 steps. I try to write it down here, and it works as follows. In the first step, we create an initial random key, for instance, a random substitution key. Then we decrypt our ciphertext using this initial key and compute a fitness score, for instance, trigram frequency sum of the putative plaintext. Then, in step 4, we modify the key, and this is very important. For instance, we could randomly swap 2 letters in the substitution key. Swap an A with an X, for example. Then, we again decrypt the ciphertext using the modified key and again compute its fitness value. And then, if the fitness is worse than before, we revert this modification since we did not get an improvement. Then, we increment a counter, and if the counter is above a defined threshold or value, we stop the algorithm. For instance, we say we want to test 1 million modifications or 10 million whatsoever. This step here is just to stop the hill climber. And in step 8, we jump to step 4. And we do it again. We modify the key, we decrypt the ciphertext, we compute the new fitness score and check if it's worse than before. If it was worse, we revert the modification, we increment the counter and do so on. So this here is the basic plain hill climbing algorithm. And now I show you why we call this hill climbing. Here I made a nice graph that shows you how the algorithm works. So what do we have here? Here on the x-axis we have the key or different keys. And on the y-axis we have the cost value of our fitness function. And when we modify the key, let's assume we have the key here and it has this cost value. And in the hill climbing step where we modify our key and then compute the new cost value, if the cost value gets worse, that's for instance here, then we change it back to this value. And then in the next step we modify the key, for instance, that we get here. And then we keep this value here. And we go on with this, and we go on with this. For instance, we then compute a new fitness value here, then we compute a new fitness value here, and finally we reach the hill. And this climbing of the fitness value is like, hill climbing. And the hill that we search is the highest hill or the global maximum. But you can also see here in this graph a problem with hill climbing or with the basic hill climbing. When we reach this point and we assume we have only 2 neighbors or neighboring keys that we can reach via changing the current key, we can only get worse with the fitness function to this point or to this point. So we reached a local maximum. The problem is we cannot get out of this with the basic hill climbing, but our correct key is here. So hill climbing doesn't always lead us to the final correct key. But to increase our chance to get the final correct key, we start at different random keys. For instance, we could start here, or we could start here, or here. It's a random selection, so we could start everywhere. And if we start close to the global maximum, we reach our maximum. But if we start here, close to a local maximum, we can get stuck. And how to improve hill climbing to get out of these local maxima, I will show you in one of the later videos. Now, as that we know how basic hill climbing works, I want to have a look at different hill climbing based analyzers in Crypto 2, and I want to show you in detail the homophonic substitution analyzer. Since here you can see live how the key changes and how the plaintext changes, the putative plaintext changes. And you will see that with some ciphers we get stuck and then we have to restart. And actually restarting the hill climber is one method to get out of a local maximum. I'm here now in Crypto 2 and I want to show you some analyzers that use hill climbing. The first analyzer that I want to show you is a monoalphabetic substitution analyzer. You just search for mono here and then you get monoalphabetic substitution analyzer. So in this template here, we have here a monoalphabetic substituted text. This here is the ciphertext. We have the monoalphabetic substitution analyzer. We have the output of the plain text. That means the decrypted text we will see here. We get the plain text alphabet and we get the key here. And let's have a look at the settings. Right now it's set to hill climbing, but we also have a dictionary and genetic attack. But I'll leave it with hill climbing. And yeah, you will see, as I said, monoalphabetic substituted ciphertext. And if we would brute force this, this would take millions of years. But with hill climbing, you will see, I press play and it instantly jumps to the result, to the final decrypted plaintext. And we had about 186,450 tested keys per second. And yeah, hill climbing is really powerful. And you see here in cryptography a substitution cipher and so on. So this instantly gives you an answer below 1 second. Hill climbing is really powerful. And now let's have a look at another example. The next thing I want to show you is the transposition analyzer. So we have here the transposition hill climbing analysis. So again, we have a ciphertext here, which is encrypted with the transposition cipher, or the columnar transposition cipher. We have the analyzer, and here we get our plaintext. Let's see if it's set to hill climbing. Yes, it's set to hill climbing. Here, this iteration count is the number of maximum steps that the algorithm would take, and then it terminates. So let's test this here. And as you can see here, yeah, that's not 100% correct. As I said, maybe it's stuck in a local maximum. So here's why he would, no, now it's the correct text. And you saw the letters changing very often. And that was based on the fact that the analyzer tests different keys, and every time it finds a better key with respect to the cost function, it puts it out here. And then you see these letters changing very rapidly. And in the end, of course, we also get the correct plaintext. And the analyzer here can achieve about 18,000 keys per second. And yeah, again, this was a very long key. I don't know, it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 25 key length. Yeah, we see here the key size also in the settings. And if you would have searched through this, you would also wait for thousands or even millions of years. But with hill climbing, it's so fast and powerful. So now let's have a look at the homophonic substitution analyzer. This is the last analyzer I want to show you. And then maybe I will have a look here at the other analyzers, or I will show you the other analyzers we also have. So here we have the homophonic substitution analysis. So here we have our homophonic substitution analyzer. We have here the ciphertext. We have a dictionary with words that the analyzer uses during the hill climbing. And we have the analyzer here. And when I click on play, I can make this a little bigger. We have here our ciphertext, and here will be our revealed plaintext. And when I click on analyze, it starts to, it's very fast. You saw it changes the letters. So in the beginning, the letters are wrong at all, and then it improves the letters over and over again until it reaches nearly the completely correct plaintext. And you can stop it here, and you can also, for instance, mark wrong letters, or you can change the letters by right click and shift and so on. But you probably already know this from my Zodiac Killer video. And I think what I will do right now, I will reset this component. Then it starts with a complete new key, and then I will let it run to a correct solution. And then I will show it in slow-mo, that you see what happens during the hill climbing. And as you have seen, it increases the cost function here, so the value gets better and better. That's our fitness function. And you see that the text gets more and more correct and that you can read some words and more words. And in the end, we have the complete plain text. And hill climbing also is a very powerful tool for the analysis of homophonic substitution ciphers. But of course, it's not the standard hill climbing. It's a highly optimized version of hill climbing with a lot of tricks that we use to improve it, for instance, to get out of local maxima. And then the final result is this analyzer here. But you can use hill climbing for nearly every historical and classical cipher to break it, or versions of improved hill climbing. And now I go back to the start center and I want to show you what else we have. For instance, we have the Enigma analyzer. This is based on hill climbing. We have the double columnar transposition attack in Crypto2 based on the IDP that also uses hill climbing. We have the Playfair analysis. This also uses hill climbing. We have, what else do we have? Monoalphabetic I had. We have the M138 ciphertext only attack. This is based on hill climbing. I think that all the attacks on classical ciphers that we have implemented in Crypto2 are actually based on hill climbing. And this was everything that I wanted to show you in this short video about hill climbing. So I hope you liked it. If yes, please give a thumbs up. If no, you know what to do, give a thumbs down. If you're further interested in cryptological topics, and if you did not yet subscribe, I would be really happy if you do so. And so, yeah, see you in the next video.